Hello. Just for fun, this one came up on Reddit just a moment ago actually, and it's quite interesting. It's the old 11 to the power of 6 divided by 3 is somehow a fraction of pi, but there's a slight twist to it. So let's show you. This is a 991 ES plus. If we do 11 to the power of 6 divided by 13, we get this number here, which it will represent as a fraction of pi, and we know that from so Matt Parker does a great video on that, but this is kind of interesting here. This is essentially 10 digits here, but this is a 15-digit calculator, and if you want to see the full 15 digits, you subtract some of what you see on the screen. So minus 136,273.9230. No, hang on, let's just do 92 and have a look at that. So yeah, so it's 307. So it said 77 on the display there, but it's actually 76923, and that gives you the full 15-digit precision. Now, what's interesting is you can also calculate the fraction of pi on here as well. So 156,158,413, and then divide by 3600 times by pi, and we get what looks like the same result, but again, if we subtract 2, 3, let's just subtract those, we get 76955. So I've got the results written up here, hopefully you can see them. You got 6923 at the end of this one and 6955. So it doesn't even think they're the same number, which is interesting. And what is most interesting is that if you subtract them, 156,158,413 over 3,600 pi, you get 0. And it has just shown you that it did not calculate these to the same amount. So you can literally take away these two from each other by hand. So this is 5.5 e to the minus 8 minus 2.3 e to the minus 8. And I don't know if you can see this all right because it's come out grey, but that is 3.2 e to the minus 8. It thinks is the difference between these two expressions. Now then, so let's have a look on the DM42, which is essentially like a reference value for this now, because this is 34 digits. So 11.6 power 13 divide, and I've got it to showing 4 decimal places at the moment, but you can show all 34 there. 156,158,413, 36,000 divided by that, times it by pi, and there we've got two different numbers. Now actually this is quite an interesting thing that's different between algebraic and RPN. When I first started using RPN, I used to think, oh goodness, you must lose all your precision every time you calculate, because you have to calculate every single time, whereas on an algebraic you're doing it all in one go. But actually I don't think that makes any difference, and I'll be interested if someone wants to show me anything different. But my experience so far is that actually these Casios will use 15 digits for each of those operators within the expression. It doesn't go more than that. The internal precision comes to play in terms of rounding to those 15 digits, but it doesn't tend to use them. Even in algebraics, use that extra precision to calculate and prevent rounding errors as you go through it. So with RPN, actually it uses its full, this has got 34 digits available precision, and it uses all of that each time you calculate it. So if I subtract these, I get this value here, 3.27 e to the minus 8. So that's the exact difference essentially between these two expressions. So essentially, don't worry about this. This was me trying to recreate the prime, which I know uses the same numerical engine as a 17B2, which is 12 digits available, 15 digits internal precision, but actually the prime also has CAS as well, so it probably mixes that in a bit. And yeah, just for fun, this is a relatively new one for me. I don't know if the battery will hold out on this, but let's see if we can calculate it on here. This has only got 10 digits precision, so I think it's going to come up with the same thing. So we've got 136.273.92 there. That's rounded to the display, it's not rounded internally. 156.158.413 divided by 3600. Divide that. Where is pi on here? Oh, I can't. Oh, there's pi. Times it like that. Get the same looking number. If I subtract it, I know what it's going to show, which is 0. But at least that is a truthful 0, and it's what it really thinks. Whereas with this Casio is essentially flushing to 0 when you subtract numbers that are fairly close. It doesn't, it can subtract a small number, because you could do 2 e to the minus 10 minus 1.5 e to the minus 10, and it can still, a subtraction can still give you a small result, but not if you have big numbers on either side of that subtraction, if that makes sense. Yeah, and I've got another video of a Texas Instrument, it's one of my shorts, where it kind of hides a slight difference in its calculation and the display, and it tries to hide it for as long as it can until you can coax it out of it. Anyway, so what's the point of this video? It's really just that things, Casios and Texas Instruments, they kind of lie to you a bit. I mean, they lie to you when they show you an irrational number as a result, when really it's only doing numerical calculations with finite precision, and so it's just trying to guess, really. It thinks, oh, it's close enough to this fraction of pi, and it lies to you about lots of little things, like when you get slight differences in a subtraction, and I don't really like that. It would also be interesting to know when the Casio actually does it. I could do some tests with that and just try and work out at what kind of threshold does it decide, I'm not going to show you the subtraction that you asked for, I am just going to call it a 0. And probably by tinkering with both sides of that equation, you can probably figure it out. I mean, a kind of similar thing is if you do tan pi on this calculator, it gives you a tiny value, 1.58 e to the minus 34, whereas on this, if you do tan pi, you get 0. And again, this is a little bit of a lie, because tan of a 15-digit representation of pi is not going to give you exactly 0, and in fact this DM42 knows that, and it's because it isn't an exact representation of pi. So again, all these, I mean, on the other hand, what looks mathematically correct? Well, obviously this one, but what do I prefer for a finite precision machine? Definitely this one. Okay, that's all.